Hey, welcome. We're going to look at 6.4, task 6.4. It's called More Ferris Wheels because we're going to look at the initial Ferris wheel that we've been looking at as well as maybe come up with some others. And in this one, again, the key information, we've got a radius of 25 feet. So I've got a little picture here that I'm going to reference. So I've got a 25-foot radius. We also have a center, the center line, which is at 30 feet. So this is at 30 feet. And I might as well write these as a point, huh? So this one would be at 0 seconds, which would be 30 feet. There's also the point that every 20 seconds is going to do a complete revolution. Again, in trig, it's assumed that you're moving in a counterclockwise direction. You can move in a clockwise direction, but if that's the case, the degrees would be negative. So degrees are going to go positive here from 0 to 360. But here we've got the time piece of it, which is 20 seconds. So we know some other points that we can plot. We know that at 10 seconds, the height is also 30. We know at 5 seconds, the height, 30 plus 25, is 55 feet. And we also know at 15 seconds, the height is at 5 feet, 30 minus 25. So we have some points, some XY values, right? And then this next piece, you're going to graph that. And what you're going to be graphing is you're going to be graphing the height. And it's a function of time, but we're going to use feet for our units. And we're going to use time as the independent variable. And that is seconds in terms of the unit. Now, in order to visualize this, I'm going to need this little guy here. You are going to be, as you're going around the Ferris wheel like this, okay, the speed in terms of the degrees is constant, the angular speed. So, for example, 10, 20, 30, 40, 50, 60, 70, 90 degrees, 180, 270, 360, 90, 180. That's constant. That's the angular speed, the speed in a circle, the angle. But there's also the height component. And what you might notice here is they spend more time at the top and bottom. So if I was to look at this right here, going around the circle, but only vertically, I would notice it would sort of pause at the bottom and the top. There's like a little pause there. Okay? The fastest part is in the middle, but at the highest and the lowest point, you can see here the steepness, it's the flattest. So I need to translate that, and so I'm going to use these points here. I also know it's a circle, so it's cyclical, so it's going to repeat. So if I start with 0 at my center line, I would be right here at 0 seconds. At 5 seconds, it goes up to 55. So at 5 seconds, 55 is right about there. And then at 10 seconds, it comes back down to 30. And then at 15 seconds, it goes all the way down to 5. Okay? And then finally, when we get to 20 seconds, it's back to 30. So again, there's a pause sort of at the top, which you can draw the fact that it slows down by drawing a shape like this. That is the sine function, and that is the cycle that repeats. So if I was to do say 25 over here, it would take me back up. And if I was to do 30, it would take me back down here. 35 all the way down. 40 right back here. So I can see that it's a repeating cycle, such as a wave function. Okay? And this is the graph, the coordinate grid graph for our sine function. Okay? Now, there is an equation that we used, and that is given here, 30 plus 25 sine of 18t. So we can generalize this by saying d D is the center. A is, it's the radius in this case, but it's also the amplitude. Okay, sine is the trig function that repeats. And then B is a conversion rate. And what it's doing is it's converting t, seconds, into degrees. So we know that since there's 360 degrees for each revolution, the time for one revolution is, in this case, it's 360 degrees divided by 20 seconds. And so therefore the angular speed was 18 degrees for 1 second. And that is the 18 over here. So now we have a generic formula that we can use for the height of t here. And really it's a generic formula we can use for all sine functions. It'll work if we change some of these, right? So radius of 20, center 25 feet on a 40-second revolution. Well, we can get a general idea what this looks like by saying it's going to start here. If it's 40 seconds, then we've got 360 degrees every 40 seconds. That means it's 9 degrees per second. That's the angular speed. And so we know it's going to drop down after 10 seconds to 5, hop back up, then it's going to pop up to the highest point, which was 45, then it's going to drop down again, and then it's going to repeat. So you can see that here's what it would look like if we just change a few of these pieces of information here. Kind of stretches it out, that 40 seconds, right? That 9 instead of 18 means it's not happening as fast. So the up and down slows down a little bit. And then they have you do some like analysis stuff. So what happens, how would your graph change if the radius gets larger or smaller? Well, if the radius is larger or smaller, that's going to affect your A value. So that's going to be your amplitude. So you could have something like this, or you could have something like this, depending on your radius. If the height of the center is greater or smaller, well, that would be the D value, and that is a horizontal translation. So based on the center height, I might have something that looks like this, or if it was very high, I might have something that looks like this, right? So it's a translation. If it rotates slower or faster, okay, well, if this is, say, my 18t, my 9t would be stretched out, and my 36t would be kind of compressed like that. How does the equation change if the radius is larger or smaller? Well, that is the A term. The height of the center, well, that is the D. And the rotation, the speed of rotation is the B value.